Great. I'm going to introduce Greg Stack from Katana Graph. So Greg Stack has 10 plus years of experience leading strategic delivery of data and technology solutions for large financial institutions. He actually worked as previously he is associate at Goldman Sachs, and he leads the credit risk analysis and also knowledge, project management and development of business strategy by utilizing big data and market insights. So now let's welcome Greg.
Thanks, E. All right, well, thank you for joining our session today. Today, we're going to be talking about using graph neural networks for credit decisioning. So the overview of kind of what we're going to talk about, we'll go through the business problem, the challenges and opportunities with that. We'll talk kind of at a high level of graph neural networks, why they're beneficial, and then we'll talk about some explainability methods. And through this, we'll go into some depth in some of these topics, but we're trying to keep it kind of at a high level to understand the business problem and really why GNNs are well suited for problems like these. So the high level problem that we're discussing today is that lenders, and these lenders can be fintechs, banks, or non-traditional lenders, they're challenged with increasing profitability to stay competitive in consumer lending markets that are growing at a rapid pace. At the core of each of these lenders' business is their credit decisioning model, and that predicts whether or not a potential borrower will pay back their loan. So one way that they can increase profitability is by improving the accuracy for that credit decisioning model. And doing so impacts the bottom line in two ways. So the first is through higher loan volumes. So as the model becomes more accurate, we're going to reduce the false positives. So that means that good borrowers that we were previously rejecting with the old model, we're now approving, and that's going to increase our loan volume. So that's going to lead to higher revenues. The second way is through lowering our credit expense by reducing false negatives. So this means that bad borrowers that we were previously approving with our old model, we're now declining, and this will reduce the number of defaults in our portfolio and reduce the amount of charge-offs that we have to take. So there's several challenges and opportunities that come with this problem. In terms of the growth of the market, the global fintech lending market is expected to grow at a 27% rate over the next 8 years to reach 4.9 trillion by 2030. And one of the main disruptions in the market is that fintechs are pressuring traditional lenders to improve efficiency and to expand to underserved borrowers. So fintechs are uniquely positioned to target these borrowers in part due to their ability to absorb high default rates because of their low overhead when you compare them to a traditional bank, but also because they can use new technology to provide a seamless customer experience during that whole lending process. Additionally, because these underserved borrowers that they're targeting, they typically do not have long credit histories, and so they're leveraging alternative data such as utility payments to make credit decisions. So this presents an opportunity to expand the number of data sources that lenders use to improve the model performance, but also presents some challenges to be able to include all of that data in a model. Another challenge that we'll talk about is that these data sources for these alternative data sources for these models exhibit varying formats. So we can have some time series data, right, if we're trying to track a consumer's performance over time. They can be static attributes, right? These are borrower attributes that don't change over time. And then one related to graph, these relational. So we're going to talk about some of these formats where we can, leverage relationships between consumers. And then the last challenge here is that historical data has become less useful in post-COVID consumer market. So because we had the disruption in the consumer market during COVID with high unemployment and government stimulus, if you have a borrower apply today, you don't have a good picture with that historical data of what's exactly in that person's credit file. So we're going to talk about how graphs and deep learning can address this issue. So graph neural networks, GNNs, they're deep learning frameworks applied to graph structured data. And we'll talk about kind of two different ways that why these are beneficial. The first is just thinking about, why is it good to model your data as a graph? And there are several reasons why that's useful. The first is that we're able to connect data from disparate sources. So again, when we were talking about, using alternative data sources, the graph schema provides a flexible way to integrate all of that data together. Additionally, if you're a large bank, you have all this customer data kind of sitting in different silos. You have communication with the consumer coming through different channels, right? That's going to be challenging to integrate into one model. And so a graph provides a good way to do that. Another reason graphs are beneficial is because of the flexible schema. So if you have changing data, you want to bring a new data source online, it's much easier to integrate that data into a graph schema as opposed to going back to a relational table and modifying the schema there. The third point here is that we can exploit untapped credit signals that exist in complex relationships. So this is what we're going to focus on a little bit later, talking about, what are these kind of signals that we can see between consumers. So applying these GNNs improves model accuracy by greater than 4 KS points. So when we talk about a KS score, the KS score is a statistical test that's used to measure the accuracy of a model. So it's essentially our benchmark that we're using. And banks will have different thresholds for this, depending on how high the KS score needs to be before they replace their incumbent model. But we've seen very good performance with these GNN models, producing very promising KS point improvements. And GNNs are able to do this improved model accuracy through learning from relationships between consumers, which we'll talk about, automated feature engineering, and then the last one is integrating with other deep learning layers. So the idea is that we can use layers like LSTM, MLP, we'll talk a little bit more about those later. And the idea is we want to capture a holistic view of the consumer's credit profile. So let's jump into an example. So this is a simple example of consumer data represented as a graph. So in this graph, we have 3 different types of node types. We have a consumer node type, a trade line node type, and a subscriber. So for this one, we have Abby, who has an auto loan through MA Credit Union. And again, the subscriber is the institution that's issuing that credit line. And then MA Credit Union also has an auto loan with Bob. So we'll talk about kind of how Bob and Abby are related. Abby also has a credit card through ABC Bank. So our task here for the credit decisioning model is we want to predict whether or not we're assuming Abby's applying for a loan at our bank. And we want to determine if Abby is a good credit or a bad credit, right? Whether or not she's going to default on her obligations. So the first step in that process to run these GNNs is we need to encode node properties as features. So with Abby, we have a lot of information about Abby, right, on her application. And we kind of represent it here with the tabular data. We know her income, we have her marital status, employment, credit score, all these different attributes that we have on Abby. And we can normalize those. So for example, for the income, we can normalize that across all values, and we'll come up, let's say it's a 0.38. We can hot encode these categorical variables. And in the end, what we end up with is a feature vector. And this is what we're going to attach to the node. And we're representing this as this little picture here. And this is Abby's embedding, right? So this is the starting point for our GNNs. The other thing, so for auto loans, the same thing. We have the balance on the auto loan, the payment status, right? Is it current? Is it delinquent? We can encode these as a feature vector and attach it directly to the auto loan. Okay, so let's talk a little bit about the graph neural networks. So the main idea behind graph neural networks is this idea of message passing. And this happens, you can think of this as a computational graph. It happens all across the graph. And it happens in basically 2 steps. The first step is to aggregate neighboring nodes. So in our example, Abby has her auto loan, her credit card. We have those features, those embeddings, right, that we're using. We're going to add those together. That's the first step. And then the second step is to apply a neural network. And there's kind of a whole host of ways you can do this, a lot of different variations of GNNs that change the type of neural network, all these different things that you can change in that box. But the end result is we have a new embedding for Abby that represents her auto loan and her credit card. And we do this across the entire graph. So by performing this message passing, our model is going to learn which of the neighboring nodes is most important in predicting if Abby is going to be a bad credit or a good credit. And it's also going to learn which of these individual features on the nodes is predictive. So you're not only taking into account the fact that she has two trade lines, but also if she is delinquent on any of those trade lines, or if she has a high balance on one of those trade lines, those types of things. So we're going to capture that in this process. So what we get is if we, so we look at kind of Abby's graph more broadly, right? We can say these are the trade lines. We can assume we have alternative data, other data sources that are attached to Abby. With each message passing layer, the information gathered about Abby expands. So on the first layer, our embedding is going to represent her neighboring nodes. But as we expand that further, it's going to capture more and more of Abby's credit profile. And as we get further out in this process, not only will we capture Abby's personal credit profile, but we'll start to capture Abby's relationships with other consumers as well. So we also know that this embedding, that Abby's graph changes over time, right? It's a dynamic graph. And so in our example, we can say that, back in January, before Abby applied for a loan, she had the auto loan and the credit card, and she was current on both of those, right? And her embedding reflects that she was current on both of those. In February, we can see that she moves to 30 days past due on the credit card. And again, that also is going to update her embedding. We're going to have a different embedding for Abby because of that change in her credit profile. And then finally, when we get to March, we can see that she's now 60 days past due on the credit card, and she's also taken out a personal loan. And we'll talk a little bit more about that pattern in just a minute. But now we've basically created three different embeddings that represent Abby's credit profile at a snapshot in time. So with those embeddings, we can now feed that into other deep learning layer networks. So for this example, we're going to use an LSTM. And an LSTM is a time series-based model that can learn long-term temporal patterns from the dynamic graphs. So in our example, the LSTM will learn from our monthly embeddings and learn which types of delinquency patterns are most predicted and whether or not Abby is going to repay her loan. Right, so we have the three embeddings here, and then we get the new one that comes out from the LSTM. And that's, again, going to learn the temporal aspects of Abby's graph changing over time. So one specific example on that, that we've observed is that as a borrower gets closer to the time of application, a borrower with bad credit will start taking out other loans. So it's not only important to capture that the borrower is taking out new credit lines, but it's also important to look at the type of institution that is issuing that credit. Obviously, some institutions will have higher credit standards than others. So if Abby is taking out new loans from institutions with lower credit standards, that should be concerning to us if we're thinking about issuing her credit. So in our graph, through this message passing framework of GNNs, we're able to learn an embedding about XYZ Bank. And XYZ Bank presumably has other types of credit extended to other borrowers. So we can effectively learn from the performance of those borrowers the credit standards of a particular type of institution. So these are some of the complex relationships that we're capturing, and especially capturing them over time as they change. The model is going to be able to pick up these types of nuances. So we just walked through an example of how GNNs can be used with other deep learning layers like LSTM. So let's go back and talk some more about some of the specific benefits of the GNNs themselves. So why do GNNs improve model accuracy? So we'll talk about two reasons. The first is their ability to encode high dimensional data. So when you traditionally look at this problem, you'll have financial modelers that will do feature engineering, and they'll say, how many times within the last 6 months has a person been delinquent on their auto loan, right? These are relatively arbitrary windows and features they can be time consuming and they cannot be accurate, right? So this is a pretty time consuming process. So through this message passing framework, GNNs are essentially automating this process of feature engineering. they're able to take in all this different information and learn which of the features are most important for credit decisioning. The second way is by learning from complex relationships between consumers. So we talked a little bit about this before, but consumers can be connected through various different paths. So in our example here, Abby is connected through Bob because they both share an auto loan through an MA credit union, right? And so the idea, that the high level idea is that Abby's proximity to other borrowers that are also defaults could increase the chances that she herself is going to be a default, right? So this is one simple example. There's lots of different ways that you can connect consumers to each other. You can have a similarity graph, right? You can actually just draw lines directly between consumers based on cosine similarity. Lots of different ways that you can create these relationships. But the idea is that the GNN is going to learn from these relationships. And these are credit signals that are largely hidden in traditional machine learning today. So an important part of this problem is explainability. You know, for regulatory reasons, when you don't extend credit to someone, you need to be able to provide an adverse action. And so having a methodology for that is important. So we'll talk there's lots of different kind of methodologies out there. We're just going to talk about one here just to get the main idea. So using backpropagation methods, we can assign important scores to the embeddings that can be backed into the raw features. So in our example, let's say that we had Abby apply, we predicted a default, and now we have to explain why. Using backpropagation, we essentially use that same neural network, and we can calculate these important scores, right, that give us numeric values for each of the features. And so based on these features, or based on these scores, we can determine, okay, the auto loan was the most impactful node in this process. And we can even further back into the raw features, right? Because we have it per feature on the auto loan. We can back into it and assume that, you know, it's because of the payment status that is why our model predicted that Abby was going to be a default. So just to wrap up, so GNNs improve credit decisioning accuracy by enabling lenders to leverage alternative data, these other data sources, to drive profitability for a growing consumer lending market. And they're able to improve the model accuracy by more than 4 KS points, and that drives higher loan volumes and a reduction in credit expense. So you have that twofold benefit. And then we talked about the GNNs, you know, why they improve credit decisioning accuracy. It's through efficiently encoding high dimensional data. We talked about this as kind of an automated feature engineering. We talked about the learning from complex relationships between consumers. And then finally, integrating with other deep learning layers, such as LSTM and MLP. And with that, I'll open it up for any questions.
Great. Thank you, Greg. We do have a question from Mike. How do you ensure that the system does not encode bias to discriminate against borrowers unfairly?
Yeah, that's a great question. So, you know, the primary way is through those explainability methods, right? So if we're able to track some of those features that are being propagated through the neural network, you know, we can track that those features are producing a bias, right? The other way is removing, you know, the other nice thing about this is we can remove the typical features that indicate that can produce the bias, right? So just starting out with raw data that doesn't have those fields can help with that as well. But then you can have that second layer where you're checking through the explainability methods to make sure that this bias is not being, you know, actively put in there.
Do we have other questions? So there is another question says, it seems some of these signals may be related to fraud or identity theft. Do you work on fraud separately?
Yeah, so typically fraud is a different use case for us, but definitely that could be some things that you would be able to pick up here, right? If you're doing entity resolution, there's lots of different tasks that could be performed upstream that could then be fed down into your credit decisioning to further give you those connections, right? So it's typically, especially in the engagements that we've been working on, it's typically treated as a separate thing, but they are definitely related, right? And you can use the same type of techniques in both of those problems.
Okay, I think that's all the question we have from audience. Oh, I have one more. How do you detect and deal with incorrect information?
So incorrect information, meaning that the data is not accurate, that we've actually collected inaccurate data.
Yeah, maybe.
Yeah, so capturing inaccurate data, I mean, that's always going to be a challenge with any model, right? If you have garbage in, it's kind of garbage out. But
Yes.
there are ways you could do anomaly detection, right? So, if you're looking through these methods, there's different things you could do kind of upstream to detect these anomalies before they find their way down into your model. But I think that's always going to be a challenge, and probably one that's handled, probably upstream.
So basically, they say credit bureau files are in theory verifiable, but they found many lost, many mistakes. For instance, traces of identity fraud or other random inaccuracies.
Yeah.
Yeah.
Yeah. Okay. Yeah, that makes sense. And I think that's the other benefit of using other data sources, right? Because you are traditionally now relying a lot on the credit bureau information. Yeah. And so being able to expand the set of data sources that you're using is going to reduce that risk, right? So I think that's just one of the benefits of expanding the different data sets, the data sources you're using.
So one more is, how do you deal with defaults that happen that you did not predict? Do you have any feedback mechanisms?
Yeah, that's a good question. So no, that's not something that we've addressed with that feedback loop, other than feeding the training data, that data back into the training data. But no, we haven't explored kind of reinforcement learning or anything like that.
Okay, great. I think this is all the question we have. Greg, thank you very much. Oh yeah, there's one more. Sorry, since we have more time. Do you monitor across key input variables the elasticity of those models to input monotonicity? Yeah, this might be this question is not very clear. Do you monitor across key input variables the elasticity of this model to the input?
I see. No, so with one of the benefits of this is that we're taking so these inputs that are going into the model, right? They're very raw features, right? So a lot of times you'll use features that have already been engineered, right? So you'll say, in my example before, how many times within the last 6 months have they been delinquent, right? And we're going to be taking a much more raw level of that data, right? So to answer your question, no, we don't do that. We really use kind of the raw input of the data, right? As much of the data as we can use as possible.
Okay, great. Thank you very much for your talk. Thank you.
Thank you.
Bye.